Okay, so here's the Zoom meeting for Physics 232C for this week. Where are we? We're right here. We're starting the fourth week of the semester. And we're studying chapter 17, which is on the electric current. Everybody knows that electric currents are important. You use electric currents every day. The reading quiz for this chapter is due today, and the problem set is due Wednesday. Now, we're not so far away from the first exam. I guess the first exam is the first full week of February. We're in the last week of January. So we're sort of 8 days away from the first exam. So keep in mind, one thing you have to do is make a quiz sheet, make a exam sheet to use during the quiz. So keep that in mind. Now, you probably already read chapter 17, but anyway, read chapter 17 and take notes. So here are some of the equations you should have written in your notebook. These are things you're going to need to do, or to use rather, in the homework and in the exam. There's the definition of electric current. We'll use the letter I to stand for electric current. It's the rate of change of charge with respect to time. So if you have current in a wire, it's the amount of charge that passes a point in a wire during some time interval divided by the time interval. Does somebody have a question? Or do you need to mute your microphone? All right, so charge has units of coulombs. Time has units of seconds. Current has units of amperes, or we shorten that often to amps. So 1 amp is 1 coulomb in 1 second. Another equation you should know is Ohm's law. Ohm's law relates the current in a wire to the change in electric potential along the length of the wire. They're proportional, and the constant of proportionality is called the resistance. So I is delta V over R. The higher the resistance, the smaller the current for a given voltage difference. So if you had some voltage difference across some length of wire, call it delta V, there would be a current in that wire equal to delta V over R, where R is the resistance of that length of wire. Now, the relation between resistance and length, it also depends on the cross-sectional area, is resistance is length over area times a constant. So resistance is proportional to length. If you double the length of a wire, it'll have twice as much resistance. It's inversely proportional to the area, the cross-sectional area of the wire. If you doubled the area, the resistance would decrease by a factor of 2. And the constant of proportionality doesn't depend on the size and shape of the wire. It just depends on what the wire is made of. This wire would have to be a conducting wire, a metal, And for each metal, there's a value of this material property, rho. Rho is called the resistivity. So let's take a look at some problems and see how equations like these are used in the homework problems. And you'll be doing the homework problems, problem set number 3, I guess it is. Some people have already done them, but you'll be doing those and you'll see them again on the exam that's coming up. So here's an example. A nichrome wire has a length L and a diameter D. It's attached to the electrodes of a battery. What's the current? Now, the unit of current is the ampere or amp. The unit of current is the amp. Its abbreviation is just A for amp. All right, so we always do these physics problems in the same way. We start by drawing a picture. So here's a picture of the wire. It has a length L. It has a diameter D. Those are given. It's made of nichrome, so it has a certain resistivity, which you can look up in a table. It's attached to a battery, so the battery will create an electric field, and that will drive a current in the direction from the positive electrode of the battery around to the negative electrode of the battery. Now, this current is actually due to electrons moving in the opposite direction. A metal is a conductor because some of its electrons are free to move. Some of the electrons are trapped in atoms or in ions, but some of the electrons are free to move, and they'll be repelled from the negative terminal, and so they'll move in this direction. They're attracted to the positive terminal. But since an electron is negatively charged, we call that a current in the opposite direction, as if there were positive charges moving to the right. Positive charges moving to the right, there is no such thing because there aren't any positive charges that are free to move. But there are negative charges moved to the left, and we call that a current to the right, or around a loop. In this case, what's that, clockwise. All right, well, we start by drawing a picture. So there's the picture. Then we write down the necessary equations. We're obviously going to need Ohm's law because we're asked to calculate the current. Ohm's law says the current is the voltage over the resistance, where that's the voltage difference between the two ends of the wire. And since they're attached to battery electrodes, that's the same as the voltage of the battery. Now we'll need the resistance. Well, resistance is resistivity times length over area. And we're not told what the area is, but we are told what the diameter is. So the area is pi times the radius squared, pi times the diameter divided by 2 squared. And we're told everything else, L, we're told V. So the unknowns are I and rho, and you have to look up rho in the table. So there's a table in chapter 17 of resistivities of various materials. Each kind of metal has a value of resistivity, and you just have to look it up in the table. Now, you're going to do a calculation, and the answer will be put in this box. It'll be a number with a unit. So what are the units? Well, when you look up rho, you'll find there's a certain number and the unit will be ohm meters. Or we write that as omega m for ohms and meters. So R will be rho, so that's this number n, ohm meters, times the length. The length is given as, whoops, lost it. The length is given as 1.1 meters. So there's the length, 1.1 meters. And then divided by the area is pi times the radius squared. The radius is 0.5 millimeters. So I have to convert everything to standard units. So I'll replace the millimeters by 10 to the minus 3 millimeters. And then that's squared. So now the answer will be a number with a unit. I can calculate the number with a calculator, but I can't calculate the unit with a calculator. But the number will be n, whatever I found in the table. This is 1.1 over pi. Here's 10 to the minus 6 in the denominator, so I can make that a 10 to the plus 6 in the numerator. And, this will be something a little more than 1, so it'll be 1.3, more or less. So this is only an approximation, but it'll be approximately 1.3 times 10 to the 6. And now what's the unit? Well, I have here meters times meters divided by meters squared. So all the meters cancel out. What's left is ohms, or the Greek letter omega. So the unit will just be ohms. Now that's R, but that's not what I'm supposed to calculate. The question is, what's the current? So I have to take one more step. The current will be V divided by R. And what's V? V is 2.5. So it'll be 2.5 divided by R. So 2.5 divided by R. So this will actually be in the denominator. So this is actually to the power minus 1, this number. And I had divided by R, so there was a 10 to the 6th in the denominator, so that'll become 10 to the minus 6. And again, there'll be a unit. It'll be volts divided by ohms. Volt divided by ohm is amp. So that'll be the current. That's what you put in the box. Now you want to calculate this more accurately with a calculator, but anyway, it'll be a something like a 1/1,000,000th of an amp. Well, it depends on what n is. All right. So that's an example of doing a problem step by step. You do it one step at a time. You don't actually pick up your calculator until the very end when you want to calculate the number. Before you pick up your calculator, you pick up a pencil and you draw a picture, write the equations, simplify the equations, and then finally you pick up your calculator. Here's another problem for chapter 17. This is in the homework assignment. Find the current in each resistor. So you have a battery. This is the symbol for a battery. And three resistors, R1, R2, R3, arranged in this way. And for part A, here's part A of the problem. The voltage is given. That's 8.8 volts. And the three resistances are given, 141, 250, and 1000. So the first thing we have to do is draw a picture. Well, we already have a picture, but this isn't a very good picture because this picture doesn't really show in an obvious way how the resistors are connected together. So we can draw a picture of an equivalent circuit, which looks like this. There's the battery down here, and then current from the battery goes through R1, and then the current splits into currents I2 and I3, which go through the two resistors. So I can draw it this way. The current comes in here and splits into I2 and R3, or I3 and I2. And then they reconnect, and the current goes back into the negative terminal of the battery. So here's a better picture because it shows R2 and R3 are in parallel. R1 is in series with R2 and R3. So here we have R1 and a series connection to R2 and R3. But the series connection of R2 and R3 has R2 and R3 in parallel. So that makes it easier to figure out what's the equivalent resistance. The equivalent resistance of this network of three resistors is R1 plus R2, R3 over R2 plus R3. It's a series of R1 and the combination of R2 and R3, but they're in parallel. So their combination has resistance R2, R3 over R2 plus R3. Now, we want to know all the currents. Well, there are actually three different currents. This whole network is equivalent to one resistor with this resistance R. So the current from the battery just goes through that one single resistor, or that equivalent resistance, and current is V over R. So this current, the current into the out of the battery and into the battery, that's just V divided by R. So that's step one. What's R? R is 141 plus 250 times 1,000 over 1,250. That's about 340 ohms. And V is, what did I say? 9, I guess. 8.8 volts. So I will be 9 over 300, roughly. So that'll be 3 over 100. That'll be like 0.03 amps. But that's not what I want. What I want is I1, I2, and I3. But that's why I draw the picture here. I can see that I is the same as I1. This current just comes out of the battery, goes through R1. And so I1 is I, which I already calculated. Now that current I splits into two parts, I2 and I3. So I2 plus I3 is I, which I calculated up here. But I've got a little more algebra to do to figure out what I2 and I3 are separately. Now, I can see here that this voltage difference from this point A to this point B is the same as this voltage difference from this point A to this point B, because it's the same point A and the same point B. So the voltage difference from A to B, on the one hand, it's I3R3 by Ohm's law. On the other hand, it's also I2R2 by Ohm's law. So I'll have I3R3 is equal to I2R2. That's the voltage difference across resistance 3. That's the voltage difference across resistance 2. And those are the same because they start at the same point and they end at the same point. And that voltage difference from this point A to this point B plus V1 is the EMF of V. So I could say V3 and V2 are both equal to V minus I1R1. Now I already calculated I1 here. I know that I2 plus I3 is equal to I. So I can use these two equations together. I have two equations with two unknowns. I can apply algebra. And so I can calculate I2 and I3. So that will go in the boxes. I1, I2, I3. So there's a bit of algebra to go through to get the three currents separately. All right. That's an example of a problem where you have a network of resistors, and there'll be a number of problems like that on the homework, and probably a problem like that on the exam, I don't know. Here's another problem which has a resistor and a capacitor in series, and a battery and a switch. So you have here a circuit which has resistance and capacitance, and a battery, that is a direct current source of current, to drive a current around the circuit after you close the switch. You can only have a current when you have a closed circuit. So with the switch open, there won't be any current. But if you close the switch, a current will flow. It'll come from the positive terminal of the battery through the resistor to the capacitor. It can't go through the capacitor because the capacitor has a couple of plates separated by an insulating volume. So there's no current that can go through the battery. Instead, charge will accumulate on the top plate, and charge will be pulled out of the bottom plate back into the negative side of the battery, so the battery remains electrically neutral. So whatever charge accumulates on the top plate, an equal but opposite charge will accumulate on the bottom plate. So you'll end up here with a charged capacitor. You remember from the last chapter, when a capacitor is charged, its total charge is 0. But it's got separated charges, a positive charge and a negative charge, separated, equal but opposite. Now this problem of the circuit with resistance and capacitance is explained in one of the sections of the textbook. So again, when you read the textbook, take notes. Let's see what we're supposed to calculate. The capacitor C is in series with a resistor. The capacitor charge starts out at 0, but at time 0, the switch is closed. Then what's the capacitor charge after a long time? And then part B of the question, how much time is required for the charge to reach 90% of the final value. When you close the switch, the capacitor will become charged. Current will flow, charge will accumulate. You'll have a current coming out of the positive terminal of the electron of the battery. You'll have a current going into the negative electrode. So there'll be positive charge accumulating on the top plate, negative charge accumulating on the bottom plate. And so the charge will increase with time as the capacitor gets charged up. So let's look again at the equations. Here's the picture. We always start by drawing a picture. Well, here's the picture. Now we write the equations. Well, the equation you need is in the textbook, in the section on RC circuits. The charge at time t will be the capacitance times the voltage times 1 minus the exponential of negative t over tau, where tau is called the time constant. And the time constant for this simple circuit was just 1R and 1C. The time constant is just R times C. So part A asks, what's the capacitor charge, Q, for large time? So let T be large. Well, then you have the exponential of minus infinity. The exponential function is 0 at minus infinity. The exponential function looks like this. If I plot the exponential function as a function of x, it starts at 1 and then it decreases to 0. So that's the exponential function as a function of x. Let's call this x. And this is the exponential function, actually the exponential function of negative x. So when t gets large, the exponential decreases to 0. So then the charge is just the capacitance times the voltage difference. The current will be 0 after a long time because the capacitor will be completely charged. When the capacitor is completely charged, then the voltage difference across the resistor is 0. Well, by Ohm's law, if the voltage difference across the resistor is 0, the current is 0. And the voltage difference will just be the same as the voltage difference across the terminals of the battery. So in the case of question A, what's the capacitor charge after a long time? Well, it'll just be C times V. Now, V is 24. C is 21 times 10 to the minus 9. So I obviously have this number wrong. This number is wrong. It'll be C times V. It'll be 21 times 24 times 10 to the minus 9. For large T. It'll be 21 times 10 to the minus 9. Oh, what's 1.68? No, that's wrong. No, that's wrong. It's C times 24. Now, how much time is required for Q to reach 90% of the final value? In other words, this is the formula for Q. The final value is just this C times V. So if Q is 90% of the final value, then this quantity in the parentheses has to be 90%, 90 out of 100, or 0.9. So 1 minus e to the minus t over tau would be 0.9. And that's the equation that you'll use for calculating the time when the charge is 90%. It depends on tau, the charging time. And tau is R times C, which are both known. So let's ask if there are any questions. Let's look on the chat box. There are no questions in the chat box. Anybody have a question? You can either type it into the chat box or just unmute your microphone and speak up.
Hi, I have a question, kind of.
Okay.
So, I've been looking at question 17.31 from the quiz, and I know it's similar to what you've just been talking about, although the equation that I'm looking at is instead of CV, it's Q0.
Right.
And
This is the case of charging a capacitor.
oh,
When
okay.
you charge a capacitor, there's a battery in the circuit that drives a current, which causes the charge to accumulate on the plates of the battery. So that's the equation for charging.
Okay, so on the one that I'm looking at, I think that I'm right in looking at that equation because this is talking about discharging. And
Discharging is this equation. Discharging is Q. I don't think I could do it like this. I could do it like this. For discharging, Q at T is equal to the initial charge, Q0, the charge at time 0. In other words, you've got the capacitor already charged up, and then that times the exponential minus T over tau. And again, tau is RC.
okay, yeah, that's the one that I've been
So that's
looking
the
at.
equation for discharging.
Okay,
And that
my
would be the case where, you charge up the battery and you got the battery the capacitor, you got the capacitor all charged up. And now you just connect like this. So the positive charge will go around and neutralize the negative charge. And so the capacitor will become uncharged.
okay.
Okay, yeah, that's another
So
problem.
trying to solve the issue that I'm running into is I think it's just an issue with like I I'm probably just a little rusty with exponential things, but I'm feeling like I'm missing a variable when I try and solve it, even though I know that's not the case.
Well, let's see. Suppose
Because
you have e to the negative x. Well, I can't do it this way. Do it this way. Suppose you have this equation. Suppose you have the equation e to the power minus x equals, let's say, a. How would you solve for x?
I would take the natural log of both sides,
That's
right?
right. So minus x is equal to the natural log of a. Or x is a negative log of a. that'll be a positive number. Because for this equation, A has to be less than 1.
Okay.
So if you're going to apply that to this problem, T has to be R times C times the log of A. X would be T over RC. So T would be equal to, this would be X. So T would be minus RC X. So that would be plus RC log of, let's see, no. Minus T over RC is minus X. So T is RC times X. So this will actually be negative RC log of A. So I have an equation like this. R has units of ohms. C has units of farads. Ohm times farad is equal to seconds. So the unit here will be seconds. And the number will just be the numerical value of R, the numerical value of C, and then the log of A times a minus 1. It might be a little easier if I look at it this way. It's plus the log of 1 divided by A is the same as the negative of the log of A.
Okay.
All right. Any other questions?
I had a question on 17.31 as well.
Okay.
So when I did the equation, I did exactly that. And when I typed my answer in, it says it's wrong. And in the book, we're using 99.9%. And I believe online it just said 99.
Right.
Do you know what percent you want us to use?
99.
So just would it be
That problem was messed up. So I rewrote it earlier today, and it's the problem as it's stated on ln kappa is now correct.
okay, so when you do the natural log, so should it be 0.99?
No, what it says is the 99% of the charge has left the capacitor. So that means you're trying to find the time when Q of T, Q of T equals 0.01 Q0. You know, it starts at Q0. 99% of it has been neutralized. All that's left is 1%, or 1 out of 100. So you're looking for the time t where the charge is only 0.01 of the initial charge. Because 99% of the charge has been neutralized. So if I look back at this equation, that says that A, if I look back here, A would be 0.01.
Okay.
So I'd have here the log of 1 over A. So that'd be a log of 100. So, you know, use your pencil and your notebook, write out the equations carefully, starting with this equation. Go through the little calculation here, and then finally you'll get an equation for t, which will involve this logarithm, the natural log.
Okay, and then in the T equation, is RC positive or negative in front of it?
R is the resistance, which is always a positive number. C is the capacitance, which is always a positive number.
Okay.
All right, so let's take a look at one more problem. Okay, so here's the final problem for tonight. A current of 3.4 amps flows in a wire with electrical resistance 10 ohms. If the current flows for 3.3 minutes, how many electrons have passed a cross-section of the wire? And it actually tells you how to do the calculation. It says, start by calculating the amount of charge that is passed through the cross-section, and then determine how many electrons would make that much charge. So, as usual, we start with a picture. So here's a picture. Here's the wire we're talking about. It's a wire, it's connected to a battery. There'll be a current that comes out of the positive side of the battery, goes through the wire, comes back into the negative side of the battery. And we're assuming that these little black lines are perfect wires with no resistance. So they're just a connection between the end of the wire to the terminal of the battery. So the only resistance is in this length of wire. It doesn't tell me anything about the wire. It just tells me something about the current. It tells me the current is 3.4 amps. Oh, it does tell me. It tells me the resistance. I don't really need to know that, I don't think. The current flows for 3.3 minutes. All right, so what we're trying to calculate using the hint, let delta Q be the amount of charge that passes through this point of the wire in a time of delta T. The delta T will be 3.3 minutes. So how much charge goes through this point on the wire, this cross-sectional area, in a time of 3.3 minutes, delta T? Well, let's call that delta Q. Now here's an equation you have in your notebook from reading the chapter. Delta Q is the current times delta T. And you know what the current is because it tells you what the current is. We're not charging anything here. We just have a constant direct current. This is a DC current. It's a constant current, not time dependent. So I times delta T. So I is 3.4 amps. Delta T is 3.3 minutes. Of course, you have to convert to standard units, so you better convert from minutes to seconds. So you multiply by 60 seconds divided by 1 minute. 60 seconds is the same as 1 minute. So I can multiply by a time and divide by the same time. That won't change anything. So I can multiply by 60 seconds and I can divide by 1 minute because those are both equal. Now, if I look at the unit here, minutes will cancel 1 over minutes. I'll just have amps times seconds. So the unit will just be amps times seconds. And remember, an amp is a coulomb per second. That's the definition of the amp. Coulomb per second. So amp seconds is coulombs. So the unit here will be coulombs. And the number will be 3.4 times 3.3 times 60. That tells me the amount of charge, but that's not the question. The question is how many electrons make up that much charge? Now, current moving from the positive terminal of a battery to the negative terminal of a battery is actually due to electrons moving in the other direction because electron charges are negative. Electron is a negatively charged particle. So this current to the right is caused by electrons moving to the left. But how many electrons would it take to make this much charge? Well, remember, each electron has a charge minus E, where that's a universal constant that you can look up in the book, or you can do a Google search or something. E is 1.6 times 10 to the minus 19 coulombs. That's the charge per electron. So if I take delta Q divided by E, that'll give me the charge over the charge per electron. That's just the number of electrons. So you can see it's going to be, you have to divide this by 1.6. This is roughly 10 to the power 2. This is about 10 to the power 2. This is about 6 times 10 to the 2. This is about 600. So this is about 600 coulombs. And if I divide by 1.6 times 10 to the minus 19, 10 to the minus 19 is in the denominator. So it'll be 10 to the 19 in the numerator and 600 divided by 1.6. So, that's going to be something like 10 to the 21 electrons. So a lot of electrons. All right, so any other questions? We've used about 45 minutes, so that's about the right length of time for the Zoom meeting. Let me go back to this. In the next few days, you're going to finish chapter 17. Chapter 18 is a little longer than the previous chapters. Chapter 18 is magnetism, all about magnetic fields. So, we've had 3 weeks on electric fields. Now I have 1 week on magnetic fields. So chapter 18, that's magnetic fields, is a bit longer than the other 3, because we've split electric fields into 3 different chapters. So this, is going to take plenty of time. Leave yourself plenty of time to read and study chapter 18. Those are the problems which are due next week. The problem set is due Wednesday. The exam is Thursday. So keep in mind, you need to spend your time not only doing the problems, but also preparing a quiz sheet, a help sheet or an equation sheet that you can refer to during the exam. So allow yourself time to do that. That'll be Thursday, not this Thursday, but Thursday next week. That'll be exam 1. All right, so any other questions? Well, then let me stop the recording.